Hello and welcome to the Code Maven meeting group and YouTube channel. If you are watching this on YouTube, thank you very much for everyone who joined us. And especially thanks Ray for giving this talk. My name is Gabor Sabo. I usually teach Python and Rust and help companies introduce these languages or introduce testing in these languages. And I also organize these meetings because I think it's very important to share knowledge and the Zoom meetings and these online events allow us to learn from each other, even if they are halfway around the world. With that, let me give the word to you, Ray, and please introduce yourself and just go ahead. One
Okay.
thing, sorry, just one thing. Those who are here, feel free to ask questions either in the chat or in the just speak up. Ray will tell you how it's going to work out. Just remember that we are recording this. It's going to be on YouTube. So if you don't want to be in YouTube, then just write. So thank you. It's yours.
Okay. Thank you so much, Gabor. Yes, my name is Ray Lutz. Let me go on to let me share my screen here so we can get started. I am actually not that long-term of a Python user, only about maybe 5-6 years. And then I had quite a wealth of experience before that with other languages, including, assembly language, C, Perl, JavaScript, all these other kind of languages in one form or another, even though I do really like Python. So I did kind of settle on that for now. And so essentially, today we're going to talk about this package called Daffodil. And it is data frames for optimized data inspection and logical processing. I came up with that later, after we've chosen the name. But the idea is that you see a lot DF. If you use pandas, you're talking about data frames, DF. And so we wanted something kind of like that, and we use DAF. So, throughout the code, if you see DAF, you know that it's a daffodil data frame instead of a pandas. I have a master's degree, mostly electronics. I did do various medical devices and document processing in my career. Most recently, I'm developing Audit Engine, which is a ballot image auditing platform for checking elections, and underneath the Citizens Oversight, which is a nonprofit organization. Now, why daffodil? We already have pandas, so why would we need something new? Well, I needed a two-dimensional data type, sort of a table structure, and so I started using pandas for almost everything. I used, these two-dimensional tables are really handy. But it turns out that pandas is mostly designed for numerics, and it uses NumPy under the hood. And so it's slow, really slow for row-based operations. And some of them are now not even allowed. So you can't do an append, like append a row. Seems like a basic thing you might want to do. That's now not supported at all in pandas because they know it's so desperately a disaster. So then you have to go over and use something else if you want to do that sort of thing. And also apply. They say don't use apply. And apply is kind of a handy thing, which means you go row by row and you apply some function to it at each row. And so you can't do that either. They said we're deprecating all these things. I think you can still do apply, but they say, it's really not recommended at all. And then it turns out also when we're using files that are kind of a weird formats, Pandas assumes a lot when it reads them in, and you have to go jump through a lot of hoops to get it to just read it in like something without doing anything, and then convert things as you go. It has some other problems too, and we'll get into that. So this is when I started looking for another data type, and I had some various ones that I started using, And I ended up standardizing on this type of a two-dimensional data frame, which is based on a list of lists. I call it a LOL. Doesn't mean laughing out loud. It's a list of list type. And so it's a Python list, and in each of these lists you have an additional list, and it's rectangular in form. So every single row is the same length, and it has a certain thing. So it's a rectangular array, but it's not the array type. It's a list of lists, so it's easy to add to, relatively easy to splice and insert rows or columns. You can do a lot of things fairly easily. Mostly inserting and rows is easy. Columns not quite so easy, but it's fairly malleable. And then also you can put anything at all in any one of these cells, and Python will handle it just fine. So you could put a whole pandas array in here if you want. You could put a whole NumPy array of 1,000,000 things in one cell if you want. Okay, so it's very versatile that way. So the basic thing is that you have this array which is just numbered, and the numbers here don't stick to the columns and rows like they do in pandas. Maybe other things. They float like they would in a regular spreadsheet. So if you move the rows around, the numbers of the rows are going to stay in the same order, even though you might have moved something up there and so forth. But then you can also optionally have names for each column, data types for the columns, and a separate type data types object that explains what those are, and then optional row keys. Okay, these are both dictionaries. So the header dictionary, HD, and the row keys, key dictionary, are a special type of dictionary, which gives you the number of the column or the number of the row in the dictionary. So I don't know what you call this exactly, but I end up calling it a keyed list. In other words, this is the key. We'll go into the key list later, but essentially this is the key, and this is the number that refers to an item in a list. And so your dictionary would have a key, and the value is always 0, 1, 2, 3, 4, and so forth. And there isn't a standard function for this in Python like there is, like you can have from keys, and you can give it a single value, and it can have nones all the way or zeros, whatever you want all the way through, but it doesn't have it automatically, but it's easy to make. So this is what it looks like. Now, as I said, the row keys and the header dictionary are dictionaries, but these are all optional. You could start with nothing, just an array of list of lists, and you still get all the functionality, but you would have to be using these indexes here. All right, let's go on to next. So essentially, what my problem was this. If you want to use pandas, and you import pandas here, and you say, I want to start a new data frame. And let's say you go through a bunch of URLs and you harvest stuff from web pages, and you want to append to this array. If you say my data frame dot append the web page metadata, you just take a dictionary and you want to add it to the bottom of the pandas array, it's horrible. And this, in fact, this has been banned by the pandas people. You can't append anymore. They just said this doesn't exist. That's how bad it is. Now, what were they doing? Why is it so bad? It's because what pandas is, let me go back a second. I got to, what is it? Shift to go back, control. I got to go with the keys. Okay. So what pandas is essentially a NumPy array vertically right here in a dictionary, where you have the name of the dictionary and the value is a NumPy array vertically. And you got to think of it that way. They're all the same length. So the NumPy array has data in NumPy arrays. The data is each value is like rammed up against each other. There's nothing else. Unlike Python, where even an integer or whatever you have in here takes quite a bit of overhead. Usually it'll be like, I think 28 bytes just to represent an integer. There's a lot of overhead generally. And if you put a dictionary in each row, then you have the key for each one. I'll get into that in a second. My point though is that in a pandas array, you have the name and you have a NumPy array. And if you want to add to the bottom, you have to create all new NumPy arrays or else add to each one. They don't let you just add each one. They create a whole new array every time. So they copy it over and add to the bottom, copy it over, add to the bottom, copy it over, add. That's how they do it. And so it takes a long time if you're appending. So they basically have disallowed this. So if you're not going to do that, then you can do this. You can say, I want to make a list of dictionaries. I call it a LOD. Okay. And it's a list of dictionaries with string keys and anything inside. And then you read the web page and you put your metadata dict and you append to the list of dictionaries. This will work fine. And it'll be fast.
Sorry, let me just say something related to this. It's interesting because I think in both in Go and in Rust, this you can allocate more space for these arrays, even if you don't use them. So you can say that, okay, I'm going to have at the end, I'm going to have 100 or 1,000 long of these vectors or arrays. Right now, I have one item in there, and then whenever so the memory is already allocated, so you can append up till 1,000 without this overhead of recreating the whole array.
They could have done a better job in pandas, because they would not need to copy over the whole thing. I didn't even know they were doing that when I first started. And so I noticed when I got, when the array started to get pretty big, that it just started to slow down to a snail's pace. And I said, what is this? Well, and then in the documentation, it says, don't do this. What you're going to have to do is create something else, a list of dictionaries, and then at one fell swoop, take your list of dictionaries and convert it into a data frame. And then it'll be reasonably fast. But this turns out is very slow. But it's way faster than appending. Okay, so if you're going through and appending to the bottom of the array, this will be faster, but then this part right here is actually kind of slow. But if that's all you're going to do and you're just going to write it out to a CSV file, then you just wasted a lot of time because you didn't need to go through this here. You could just write it straight out. But if you did do a couple of things with it before you did that, you maybe summed everything one time and you added everything up. Maybe you did some other manipulation and you thought being in Panda's world was a good idea. But then you had this overhead of doing this. So this works, but it turns out this is very slow. And when you time it, going from a list of dictionaries into pandas, well, this is a 1 million integer table, 1,000 by 1,000. Okay, that's the size table that we're using for our benchmark. Now, would pandas normally have 1,000 columns? No, right? Because most most data tables have very few columns. Usually, 20 to 30 columns is a big one. For the data tables I'm working with, they have a lot of columns. Okay, it's like something with 5,000 columns is pretty big, but you'll see stuff under that, and a lot of it 300-400 columns. So 1,000 by 1,000, not unusual that I see. And when you convert this in Daffodil, you just take the list of dictionaries and make a list of lists with formatted for Daffodil. It takes 139. What is it? Microseconds, milliseconds, I believe. Pandas takes 5,600, more than 5 seconds. More than 5 seconds to convert it into pandas. So it is a ridiculous bottleneck. Okay. It takes 139. Like, look at the difference here. And if you multiply this out, even though pandas is really, really fast to do certain things, like summing columns is ridiculously fast compared to Daffodil. I can sum columns here at 191 milliseconds. It takes only 4. So that's a big difference. So you do a big savings here. If you do a lot of these, then this might make up for this big difference here, but it takes a lot. It takes at least 30, all columns, doing all columns, all sum, standard deviation, da, 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 da. You got to do 30 of those before you make up for converting it into pandas. So for just a few things like summing columns or something, or just manipulating the data a little bit, you're just better off not getting into pandas because of this ridiculous conversion factor. Now, I tried to get around this problem here. And there's also another problem with pandas. This is integers. As soon as you add a string, and this is the size. So the size here is 38 megabyte, believe it's megabytes, for a million integers. And they're only at 9.3. So it's quite a bit more compact in a pandas, right? If you have just integers or just floats. But if you get a string, then this goes up and becomes quite a bit larger by 10 times. And quite a bit larger than a daffodil table, which really doesn't go up very much. Okay, so then, NumPy, we can convert things to NumPy really quickly, 48 milliseconds going to NumPy and from NumPy doesn't take very long. And then you can manipulate in NumPy. One column at a time, or add columns together, or sum the columns, whatever you want to do. You can then do it directly in NumPy and skip over pandas. Pandas is also a big beast. It takes a long time to load. So if you use daffodil, you import daffodil, and then you create a daffodil array. You can't click on this or it goes to the next thing. I can't highlight for that reason. But you create a daffodil array, my daff, and then I go through the URL and I get the stuff and I append the dictionary to the daffodil array. Done. And then I simply write it out directly and I skip over this thing here. Now, I was in a bad habit of using these pandas arrays for almost everything because they're so handy. But little did I know that my code was getting to be really slow because of the conversion of the list of dictionaries over to pandas was taking a long time every single time, and then back. So this is when I came up with daffodil, and what it provides is a way of also indexing into these. Now, if you just used a list of dictionaries, if you think about it, you have for every single row, the keys are repeated, and then the next row, you repeat the keys, and you repeat the keys, repeat the keys. So every single row has a lot of overhead because the keys are being repeated. So when you crunch that down, if we look back at the data type here, and you see in the row here, it's only that for each row you just have a list of values, and you don't have the keys. The keys are one time only. You don't need them every single row. So you crunch all the keys up into one row, and then the indexing goes two times. So first you get the index of the list, and then you index into the list to get the data item. So it's one more step to get to it. But these are lists. And there's a lot of benefits to that. First of all, we can use this type of indexing in Python, which they provide all this as part of their infrastructure so that you can write code that uses the indexing row column or you can use it for anything, but in this case, the first index is row and then column. So the row and column can be integers, and that can be either the array index or it can be if you want it to be, but you have to go through. If it's an integer, it assumes it's going to be the array index and not going through the dictionaries. If you want to go through the array indexing, you have to use a method. But if it's a string, then it assumes that it's a key into the dictionaries. And it can be a list of integers, which then is the list of array indices that you want to choose. It can be a list of strings. It can be a list of string of keys. So you can pull out individual rows, individual columns, whatever you want. You can index an individual position in the array. You can slice and dice it. You can give it a range of indexes like 5 to 10, which gives you 5, 6, 7, 8, 9. Or you can do a range of keys in a closed kind of, which we use the tuple for that. So it's like from C to AB. So from like column C to column AB, because you don't know what's after AB, you can't say go to the next one and back up one. You have to give it a closed range. And so we do it like that. Now you can leave out the column if you want to use all columns, kind of like star and SQL expression. But you can just leave that out and then talk about the row. And you can index in, if you append, the things can be in a different order and they will always go in correctly and to the right. So here I have it screwed up where C is first and it ends up putting C in the right thing. And there's all kinds of examples here of how you would take that array that we start with here, 1, 2, 3, no 4, 5, 6, 7, 8, 9, 10. I don't know why I did that, but then you end up saying I want to use rows 1 through 0 and 1 because that's a slice. You get those. You can get the columns. Same way, you can use the names of the columns, take all rows and names of columns here in a list, so forth. We also offer a list of tuples. I'm sorry, a list of ranges, which is kind of handy sometimes. And then you can set a value. You can say, I want to set this value to the entire array. It sets the whole thing. You can set the first few columns. You can slice it and do this. So this is a setting. So you can set, and you can also pop in a list. Like if you have a list, you want to put that in the column, you can put that in. You can put a list into the row. You can put another daffodil array in and it will put in that for, whatever the rectangular region is, boink, can put that in. All those things work. Now there's a return mode, which is optional, but we're going to end up putting this into, like when you do this indexing here, you want to get the value out in this case because you want to multiply two values together. If you set the return mode to val, then it'll give you the value directly. If you just did this, you would get a daffodil array of the cells 0 and 1. I'm sorry, 1, 0. So it would be row 1, there's row 0, row 1, and this would be 5, right? And you would get an array of 5, one thing in the middle of the array. Well, you don't want that. You just wanted the value. So if you said return the value, then you can just multiply it by this value over here and put that. And the one at 2, 2 is 0, 1, 0, 1, 2. 0, 1, 2 is 10. Multiply those together, 5 times 10, and put that in the cell 2, 1. And down here, 0, 1, 2, 1 is 50. So we multiplied those values together and put it in here. So it's all malleable. You can do it like that, just like a spreadsheet. And then we can insert columns here. So we're going to put in a first. So if you add a column like house, car, and boat, and we call that category, then we also say we want to set the key field to category. Now, what it's done is, what it does is one of the columns you can say that's going to be my key field, and then it puts it in that dictionary lookup called the DK. Let's see, it's called HD. It's called a key dictionary. So this is a dictionary lookup, so it's super fast if you have a long one. But it has to be, if you do this, you can't have repeated values in here. It's gonna hit the first one that it sees. And so here what we did was we add additional records, and it's going to add them in there with here you see the category is in a different order, and it still puts it in. And if we have a double, in there, it's going to modify the one that's there. So if you index in and you say house, car, boat, and house, car, boat, mall, van, condo, I think I have it in the next one, where if you say house and you give it new values, it's going to modify the one that's there. Okay, so it doesn't add another one called house. Then you can select by using a select where statement. This is where lambda statements are really useful, where you just say lambda row and you say the row where the C value is greater than 20. I want to select those rows. It makes a new daffodil table, but it doesn't make new rows. These are actually the rows from this table just referenced over here. So it uses a by reference, just like Python does all the time. So you're not actually creating a new whole table. These are not unique values. These are actually the same list values from over here, put in over here, so that you've just selected them. And so this daffodil table only has a list of references to the same data. All right. So that this way, these selections are very fast because it doesn't do any copying unless you want it to. Okay. You can select a record by the key. You can also just do it this way. Put the key into the indexing and then say you want it to be a dictionary. Now what we're going to end up doing is putting comma in here. Whoops. Can't click. You put a comma in here and put a R type, return type equals dict inside here instead of having .2dict, because it's handier to know. Like in this mode, if you want it to be a list, that's what is already in the array, the list. So if you want the list out, you don't want to convert it to, say, a dictionary or a whole array, because you're going to get a whole array out of this selection, one row, but it's going to be a daffodil array data type. So what you don't, if you want to get a list out of it, it's nice to know ahead of time. So I'll show you that in a second, because there's another thing I want to show you, which is called a keyed list. So you can get at different types out. If you have two list, two value, you can just print that. Or there's other things, to NumPy, to pandas. There's other things you can convert to here. So a common usage pattern is to process things by row, where you would have somehow you're transforming the original row into a new row. And then you append the new row to the new daffodil table. Now, depending upon what the transform does, it might give you the same data again with just something modified. It might mutate that row and you would get it back here. When you append this, it's the same row as the original with a mutation. Guess what? That's going to modify the old row. So you don't necessarily want to do that if you're making a mutation. And then you would append it to the new table, and then you can put it out. It turns out you don't have to flatten, we discovered later, and I want to show you that in a second. It automatically flattens. So you can just apply. So if you have a transform row function, you just say apply the function, and it applies it row by row, and then gives you a new daffodil table. So you can do it this way. And you can also then just apply the data types at the end if you want. Like, you can read it in, apply the data types, apply the transform. You don't need to flatten it anymore, because I'll show you why most of the time. And then you just say to CSV and write it out. So here's where you write it in and you transform row by row. If you're doing this, Daffodil works really well. Okay. And this same sort of transform can be applied to, I'll show you in a second when we're expanding this to use SQL backing. So we avoid copies. This is what makes it faster, way faster than pandas most of the time. Pandas is fast if you're doing those matrix they're array manipulations that are used in NumPy. But if you do stupid things like have add columns and add rows and pen things and stuff, it gets really, really slow. And also when you end up copying. So we're using references to existing data rather than recopying, unless you want to. So row selections reuses the existing header dictionary and the selected list values from the source daffodil array. And then processing by columns is slower, but you can usually avoid that. What you want to do is in one fell swoop, if you want to add columns and drop them, you do that all at one time. And in fact, if you want to do if you want to flip the array on a diagonal, which is why can't I think of it? It starts with trans. I can't think of it. Trans. We'll get to that in a second. But the daffodil's pretty slow with doing when you know head to head when you're doing manipulations of numerics. But when you're doing this type of row selections, it's much faster. And column basing, it's transposition. If you say flip is true and you're doing adding rows or subtracting them, you can also flip it for free because you have to make a whole new one. So you can flip it for free if you want to when you're changing the columns, dropping them and adding them. But you want to do that all at one time, add and drop, basically modify the columns, end up with a new array that has the columns that you need, and then mutate it in place. In other words, don't add columns one at a time. And because that's going to just be a lot of overhead. But if you have columns in there, then you can just don't use the ones that you don't want to use. Okay, next thing. So the keyed list is one of the core technologies that we developed inside this once we got some more experience. So a keyed list is basically if you do a zip of keys and values, this creates a conventional dictionary. So you have, if you want to, let's say you have a list and you have keys you want to apply to a list values. You have to go through this transformation, and this takes time. It distributes the values to each item in the dictionary. So you create a dictionary with these keys, and then you put a value on each one. And it's in memory. Now, all of a sudden, the values are distributed out in this dictionary. You don't know what order they're in, or in some weird order now. The dictionary takes care of making them in the same order, but in the actual dictionary itself, I don't know what order they're in. They're not a list anymore. Let's put it that way. So you can get the list out by saying dict.values. You can get the list out, and you can get the keys out. It's not a list at this point. You'd have to convert it to a list. It's a keys type. Oops. So we propose this concept of a keyed list, which contains a header dictionary that contains the indexes for each key. And this is one way to create the header dictionary. And this is an easy way to understand it, but it's not the most optimal way to do it. So you're going to have a column name and the index for the index in the column for the enumeration of the keys. So this index is going to go 0, 1, 2, 3, 4, 5, and that's going to be the value, right? You go through all the keys and you put them up here. So this stays the same for every keyed list of the same size and with the same columns. You don't need a new header dictionary. You can use the same one for different keyed lists. And the list is a list. So unlike a regular dictionary that distributes the values amongst all the keys in the structure, the list is still a list. It still looks like a dictionary. You have a key and a value, but it's structured and you can still get the list out. It looks like a dictionary, but it's not designed like a dictionary. It has a header, which has, excuse me, like A0, B1, C2, and then a list associated with that. And that this way it's faster to do things. So if you have a keyed list and like A is 34, B 45, and C is 56, and you have values here, 1, 2, 3, you can say the keyed list dot values equals this value list. Assign new values, and now you have a new keyed list with those values in there. You could do the same thing with a dictionary. would put new values into the dictionary. If you say, what is the value of B? You're saying I want to assign 67 to the B. Now you have 67 here. The values list that you originally used, sorry, I can't click. The values list that you originally used also got changed because it's the same list. When you said, I want to assign this values list to the keyed list dot values, it did not make a new list. It did not recopy anything. All it did is add a reference in here to this existing list. And then the values list is the key list dot values, output true. The is function means it is exactly the same thing. It's the same thing in memory. There's no new version of it. So a keyed list means that we can, number one, if you have a list and you want to put it into your daffodil array, don't turn it into a dictionary. Like if you have a list, it goes directly into that list in the array. Now, if you want to iterate through the daffodil array, it's convenient to iterate through with keyed lists, because if you modify one, it actually modifies the array without having to recopy it in. Just the way like if you had a list of dictionaries and you go through the list of dictionaries and you have a dictionary in hand and you change that item, it actually is the same dictionary as in the main array of list of dictionaries, and it'll change it in the list of dictionaries. Now, if you have a daffodil array and you pull a dictionary out, it's not the same data as what's in the array. And if you change it, it doesn't change what's in the array. But if you take a keyed list out and you change that item in that list is the same one as in the array, and you've changed it without having to recopy it back in. So then it works the same way as dictionaries do. I don't know if I probably can add another slide for that to explain it. Now we're going to go to a new topic, CSV reading. Very, very fast if you have, as you stay in string type. So as long as you don't convert anything, the Python reader is really fast. For 1,000,000 rows, according to this guy here, this reference, he timed it. I'm not sure I trust this, but anyway, I used it because it was a reference. And if you do a pandas read CSV, it's much more time. Pandas read CSV with a chunk size is, for some reason, worse. Dask, worse. Data frame. Data table, I guess, is another option. It's not as fast. This looks like absurdly way better than it really is. So I'll have to look into that. But it's still very, very fast because it doesn't do any type conversion for you. And Pandas does this automatically, try to be easy to use. But if you don't want that, it doesn't happen. So later, you can apply the D types and unflatten them, which would bring them up into become a data Python data type, such as like if you have a dictionary in a cell and it gets turned into what either JSON or what I call Pyon, which we're going to get into in a second, then it will reform that into the dictionary within the cell. Now, CSV writer flattens automatically to Pyon. I didn't know this. Pyon is something that I dreamed up as a name. It means Python object notation, and it's similar to JSON. It's actually a superset of JSON. JavaScript object notation is JSON, and this is simply Python object notation. But it can express sets, tuples, dicts, lists, functions, etc. So it can do everything within Python, and it already does for the most part, except for functions. It'll create sets, tuples, dicts, and lists automatically in a CSV writer without you doing anything. I just stumbled across this. Now, Pyon already exists. It's already defined. It's what you get if you repr something. Generally speaking, not always, because sometimes the reppers are broken in these things. But what they should do is define this as being, as CSV writer should use repr. And sometimes it uses the str function instead. It's better than pickle, JSON pickle, and other variants of JSON for working with Python types, in my opinion. So I generated this Python tools Python module. It isn't quite published yet, but I'm using it myself. And it turns out CSV, but it's very simple, because what you're doing is you're using the repr method for any object, and it basically does it already. But when you're using CSV writer, you don't have to change this. So the way I stumbled across this was I had dictionaries in my daffodil array. I wrote it out to a file, and it automatically converted them and flattened them out into character strings, the normal ones that you see. When you look at a dictionary, like we just were looking at some that look just like, when you look at this dictionary right here, open bracket, single quote, a single quote, colon, 0, comma, all that sort of thing. This is the expression, a string expression that represents a dictionary. It isn't the dictionary itself. The dictionary itself is some other, thing in memory, and of a fairly complex structure that Python has suppressed. And what you understand as a dictionary are these symbols right here. Those symbols are character strings that can be represented in a file. So this is what you get. If you have a dictionary, which is this header dictionary with those things in it, that's exactly what you find in the CSV file, this right here. Unfortunately, it doesn't use double quotes, so it's not exactly JSON. If they allowed you to say, use double quotes instead, this would be JSON. And then you could use it with other tools. A little bit of a ripple there with what they use in Python. And maybe we can get CSV writer to optionally use double quotes, so it would still be valid Pyon, but also meets the subset of JSON. I think the Python community should embrace the Pyon that they've already defined, but they don't have a name for it, and provide options for CSV writer to use double quotes and stuff in there, because then it would produce JSON. But this is how we flatten things from Daffodil. We almost do nothing. Python already does it for us. Now, when we import CSV, we do it in a very controlled, explicit manner. So it comes in as strings, and then we convert them. Unfortunately, Pandas is optimized for tables with just numerics and simple header, normal for CSV, and it's hard to work around this. You can do it, but it's just a pain in the ass to try to get it to do weird things. So what we do is it daffodil D types, which is something you can specify. It doesn't do anything. It just gets carried around in the frame. But if you are importing things, you can say apply it, and then it will apply D types to the columns that you want to apply to. If the columns don't exist, it's not going to hurt it. If you drop them, you don't want to apply D types to any columns you're not going to actually use. So if you bring in an array and it's got 5,000 columns, you only need 3 of them. First, drop everything else that you don't need, or just work on the ones that you want to work on. In fact, you don't need to drop them. If you brought it all the way in, just work on the columns that you want to work with, and then just ignore the rest. As soon as you start converting the thing, then you're starting to add time. So we have a few other features I want to mention. Number 1, we have an indirect functionality, where a dict can specify the contents of specific columns. So inside of a cell, you have a dictionary, and that dictionary actually specifies column names and values, which are to be interpreted as part of the actual array, but it's got an indirection. So you first go into the cell, you find out what's specified there, and then that's to be interpreted as the rest of the array. And this is useful for sparse arrays. As I was saying, what I was working with was very sparse array with like 5,600 columns, and only about 50 of them are used at any one time. So yeah, if you represent this as a actual CSV file or an array like that, it's very, very costly because you have all these commas, right? Comma, 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 comma. And to represent all of the 5,600 columns when you're only going to use 50, and then you have them in there and you got to try to figure out which ones they are, it's a mess. So in this case, even though you want the array to be logically 5,600 columns, for any one row, you don't want to have to specify more than just the 50 columns that you're working with. And so in that one cell, what you have is a dictionary which specifies all of the columns that you're working with, and then it is logically considered part of the array. So if you sum the rows, it figures out where it takes that indirection into account, expands them, and works with summing them that way. We have a from PDF that will take a PDF file with a header and columns and parse it, usually skipping a few things. There's a few controls there to skip things, but to just convert from basic PDF files that you might find. A little shortcut. You can do it yourself, but this shortcuts some work. It offers the adders attributes ATTRS dictionary as part of the class for an instance. Has this, and this is the same as in pandas. You can add any kind of attribute you want to a data frame. And what I find is convenient there is like if I've already figured out like these are the metadata columns, they're all strings, and the rest of it is data. Once I parse that and I know where they are, I need to pass that along and say, these are the metadata columns. This is the number of columns, that's the metadata. And that's easy to do. You just put that into this adders, and then your next function says, well, how many metadata columns are there? Oh, it's in adders. I already know that. Now you have to know that it's in there. But at least you don't have to pass another variable along to say here's or recalculate it, even worse. So that's something that turns out pandas had, and we just using that the same way. And then we're now offering a join method that is efficient and mimics a join in SQL. Pandas doesn't have a real join. It has a merge. So when you do a merge in pandas, you do this, you essentially are doing what this does here. But and I'll get to this in a second, we're extending daffodil to use SQL in the background. And when the SQL machine does a join, it doesn't actually do anything. It actually just keeps track of the join. And if you say, I want to take these columns in this table and I want to join them with these columns in this table along this key, it doesn't do anything. It just remembers that. And if you say, I also want to join this table in, this table in, this table in, this on these keys, you can do them one at a time. And you can do up to, I think, 64 times, or maybe it's 16, but there's a certain limit. And then once you have all your joins done, and you say, I want to select these rows out of my join tables, then it does it. Then it figures it out and it pulls all the data in and does it. Okay. So it's nice that way that SQL, when it does a join, it creates a view. It doesn't actually it doesn't actually do anything. Now, Pandas always does something. It always does a merge. It takes data from one thing, it puts it with this one, and merges it together. Essentially, that's what this join does. But this one will be using the SQL type of join when we get to that. So there's the plans for SQL. Now, right now, daffodil arrays must fit into memory at this time. So if it doesn't fit into memory, you're going to have to chunk it, which we do. So we have a thing where we chunk things, and there's a lot of infrastructure. I might add a daffodil that chunks things. So basically, if we have a chunk of like 100 things in one chunk, and we have thousands of those, we don't actually want to combine them necessarily up front. Maybe combine them all at one fell swoop and then make one big file, or just work with the chunks. What we'll do here with SQL is since the row-based daffodil arrays are similar to SQL, data tables. They're also row based, but they have column operations, of course. We'll add quarks. We'll add additional keyword arguments in the indexing to specify whether it will be an SQL table, or another way to say it is just you take the original daffodil dot to SQL and we'll give it a name, and then we'll get this daffodil table main underscore SQL daff. We'll just call it that. You don't have to use this name. And that will be how we refer to it within Python. And this actually will look like a daffodil table, but it's actually in SQL. So we don't actually have the table in daffodil. It's basically a proxy to the actual table. Then operations on SQL daff will operate as if the table were in memory, but it actually is operating the SQL engine. And the results is we can allow much larger tables while still manipulating the daffodil array paradigm with selection and indexing done in a Pythonic way. So essentially, we're still going to use those square brackets. You know, the first one is the row. Well, that's like select, the second one is column. So select star, that would be kind of like the second thing, the columns that you want. And then you say which things you want to select in a SQL statement. That would be the first parameter in selecting it, and the like. So I won't go into some of the difficulties that we found in SQLite, but SQLite does not have a row-based, like a vector-based operation, so that we can have Python and apply that would take, say, a row from the table, run it through Python and return an entire row and then add it to a new table. It doesn't provide that in SQLite. That would be an extension we'd want to see. All they allow is scalar returns, and then it's a lot of work to do it. So it's better to bring a chunk out of the table as a daffodil array, apply it within Python, and then move it back into the SQL array. That's the best way to do it right now. It's the fastest. So once, if you want to use, we would also support general SQL queries and the proxy. So if you say I want to actually use this SQL query, then I keep doing that. Can't click when I'm in this. So if you want to have an SQL query and apply it to this proxy, we don't know the name of the table over there necessarily. And one thing about Python is when you create a daffodil table, you don't know what name you're going to apply to it because it's not the way Python works. It doesn't know what name it has. In fact, it can have many names. In SQL, when you have a table, it has a name, and you have to use that name to refer to it all the time. So we're going to have to name our table with some arbitrary name if you don't give it one. And then or we may actually always name it with arbitrary name and then map it over. But essentially, when you do an SQL statement and you say, I want to like select blah, blah, blah from, you have to put in a table name, okay? And you're not going to know what that name is. And so that's why we're going to have some substitution going on with that. And that won't be too hard for people to do if they want to use general purpose queries. Pretty much everything within Pandas is available within Daffodil. But some things that are not available in Pandas are available. Like we can do append, which has been deprecated. But most things run the same way. A little bit different because Pandas is normally columns of NumPy arrays. And so the first value in the square brackets is a column by default, whereas in our mode, the first thing by default is the row. Just to be aware of that. And so pretty much they're all there. And again, the timing we went over briefly at the beginning. Daffodil is faster for array manipulation, like appending rows, but Pandas is faster if you're going to do column-based manipulations. Basically, here was my summary about use cases and when you want to use each one. If you have existing data in well-defined column-based format, then and almost all data is numeric. And you don't want to do appending or pontification other than maybe creating some additional columns, and then maybe produce plots after you analyze it and so forth. Then pandas might be the best choice for sure, as long as the data fits in memory. Once it gets out of memory, then maybe you're going to use daffodil SQL might be a good choice. We'll have to see. That haven't really tested that enough to know if that's going to be a better choice for you. If you're building data tables by analyzing and converting images or other data, appending to a table, that is not going to be pandas. If you want to have small utility tables used for tracking processes or parsing data, driving state machines, all these kind of little tables that you might use all the time throughout your code, use daffodil tables. Don't get involved with pandas. That's for data analysis and those specific things. Once you build the table, then you might want to use pandas or NumPy. We can convert individual columns, and this is a pretty good way to do it. Convert it to NumPy arrays so that the columns can be managed. There can be, sum, for example, like if you sum two columns, you get another whole column. This kind of operation here will work if it's a NumPy array, or you can multiply columns. You can do all of the functions, add them together, multiply by a scalar. You can, all of these functions here, or say divide one column by another one, it creates another whole column. And that expression is very fast. So you can do this by just having a dictionary of NumPy arrays converted on the columns that you want to use. If you want to do state updates like tracking the state of a user in a web-based application or something, then you're going to want to use an SQL or NoSQL or something kind of database, and not use any of these, of course. Statuses that, I've used it quite a bit myself. It hasn't really been adopted very much. That's okay. I mean, we're still sort of researching the best ways for this to work. I've used it myself. I've converted almost everything over from pandas, and I love it. In a couple of cases, I still have to use SQL because the tables got big, and so that's why I want to convert over to daffodil SQL. And that's pretty much what I had there. Okay, so I'm done. Guess my contact is raylutz@cognisys.com, or you can, that's my email. Any questions? I guess I used up the whole hour, a little bit more, and not gave room for many questions. I see a chat room is on.
Yeah.
Okay,
I,
only thing, apologies.
right.
No worries.
I don't
Any
really have a
questions?
question. If anyone has questions, then please do ask. I just wanted to say something. First of all, thank you very much for the presentation. But one thing that is sort of related, that I see many people using pandas for I just read in the CSV file and do some simple manipulation, and they always go to pandas because that's what they learned, and they don't
Yeah.
use the standard CSV library.
Yeah.
And I didn't. I had a feeling that pandas is just way too big for this, but now your numbers show that it's way slower than using the standard CSV library.
Way slower, and also just getting in and out of it. Like
Yeah.
if you're just staying within the pandas world and you're doing stuff that are pandas related, it's great. And I think though that what we're going to find is that using a daffodil array and converting it to a dictionary of NumPy arrays, which is kind of what's inside pandas, but pandas has grown so big that
Yeah.
I watched it load. It takes several seconds, maybe like 5-10 seconds for it just to be imported. So when you're running one of these interpreters and you're using a huge library like pandas, I mean, the main pandas class, just one class, is like 13,000 lines. It's all in one file. I mean, I'm really surprised they still write them this way, but it's a very highly functional thing. And here's the thing is that people are nowadays, they might be using an AI machine to assist them, and they say, read this in and do a few conversions and then help me do this plot. the AI machines, they know perfectly well how to use pandas, and they'll do it. Now, for that, efficiency is not important, really. You may wait a few extra seconds, but who cares? So, and daffodil is a little bit different animal that actually is all Python, and not that pandas is not. Pandas is NumPy, and but it's restrictive in what it can put into its list, and it's designed around numerics. So when you start adding strings or anything else, it just freaks out. It's just like you're just going to have to. Then you got to go back to a dictionary of lists, or list of dictionaries, I mean. And that's what I ended up doing. But then I didn't have the functionality of selecting rows and other things that you want. Now, will this catch on? I don't know. I think that for most people, I mean, I still like to use pandas for certain things just because I know that the AI machine knows exactly what to do with it. Once the AI machine understands Daffodil, it might do it, but I don't think it's really the use case. Daffodil is more for programmers than for people who are data analysts. It's more for somebody who wants to program in that use these. I mean, I use them all the time because if you don't use one and you know that it's not suitable to use pandas for this, so then you want to refer to a column of the array. Well, it's a list of dictionaries, so you don't have columns. You have to go through and write a comprehension that pulls out the column. You can do that, but it's easier just to have something that's all well tested and everything that pulls that column out, makes conversions and so forth. So it's a handy thing to have, and I think it's logical to have a next step up. So we have fairly high level data structures in Python, such as lists, dictionaries, very highly functional and really nice. But we need to move up a level and have a two-dimensional functional data frame within the Python world, and not make it NumPy. Not that I'm against NumPy. It's just that it's very restrictive as to what you can put into those cells. You can put some strings in. I think it's up to 20 characters or something. So, okay.
Okay.
All right. Well, thank you so much. I guess you're right. It's most people, I think, are going to say, well, I'm just going to continue to use Python pandas because that's what I'm used to, and I don't really care about time so much as what you're saying here, and I'm not doing appending. But if you're doing the appending, if you're building these tables up, that's when Daffodil becomes a pretty handy little tool. Okay, thanks a lot, Gabor. I guess that's the end.
Yeah. So thank you again for giving this presentation. Thank you everyone who were present and listened to the presentation. If you like the video, then please like it and follow the channel. And see you next time.
Okay,
Bye-bye.
thanks a lot. Okay,
Bye-bye.
bye.